Okay, I wanted to see if we can try to help you all a little bit with labs. I know labs can be tough, and so I thought I would kind of broad brush some areas. I know, for example, one of the labs we're talking about has satellite in it. So let's just take a look at satellite. You're going to be seeing satellite in more labs going through things, so we might as well, explore it a little bit. I'm just using one of the many possible curves for satellite. And this image is centered over the United States. It's going from goes east, which is mainly looking at the eastern half of the United States, but can also see some stuff on the west coast. You can see up in the northwest a greenish area. This is a water vapor, mid-level water vapor curve. So what that tells me is I'm looking at some moisture coming up out of the South Pacific into the Midwest. And I'm seeing some moisture coming out of the South Pacific into West Texas and up into areas, maybe in Arizona, New Mexico. With that, there's a lot of dry air coming across through this area of the United States here. Uh, there's some moisture up here, but very limited. Notice some moisture being pulled back into this area. There's actually a low pressure system developing right here. Not a lot of moisture with it, but you can actually see the circulation there. So one of the nice things about water vapor images is when you look at them, you can see circulations in the atmosphere. And so with that, just taking a look at circulations, and these are areas typically they're rotating counterclockwise, means they're low pressure areas. So I have one here over the Carolinas and Southeast Virginia. I can really take a broad picture of it right here. I have another one out over probably Utah, right in this area. So kind of neat to see these. If you can pick them out, think about it. We're going to get into that upper level low pressure areas kind of influence the surface. So with that, I have in front of you some information that could be useful in that. So this is just some way of looking at this satellite images. The idea of looking at satellite images is to try to spot interesting weather features. Interesting weather features can be circulations, can be different levels of clouds. Instead of looking at this information, maybe I could go to an infrared image and we would see long wave radiation, which is infrared, and we'd notice there's some higher clouds right in this area. But notice a lot of low clouds back across Virginia. Oh, yeah, in West Virginia here and in Ohio, there's some low clouds with things. These are not high clouds because they don't have infrared image uh, coming up. What we do is pick certain temperatures and begin the curves at that point. So anything below a certain, above a certain temperature is not going to show up on the infrared. We want colder and colder cloud tops. The colder the cloud tops are, the more enhanced the clouds are, the higher they are in the atmosphere because the troposphere does cool with height. So you can see we can differentiate using satellite between low and high clouds. So that's just a touch on satellite image. So let's take a look now at a station model. All right, so I want you to really understand these. These are so important. So I don't care where I pick here. Let's pick Beckley, West Virginia. Left hand, upper corner, 35 degrees. That is the temperature. The dew point is the lower left, and that's 31 degrees. So that means that the temperature and dew point are relatively close to each other. 4 degrees is relatively close. However, the further apart they are, like there will be some instances where the temperature and dew point temperature might be 36 and the dew point might be 10, that's very dry. But now we've just looked at two things. What's another thing we can look at? Well, we know pressure. Pressure is the upper right here. And yes, I'm being nice to you. I put the 10s in front, 1019.8. If I were to knock this 10 off on most surface weather maps, all you would see is 198. You've got to add that 10 back in. Remember, I said if anything is below 500, the odds are you're adding 10 to the front of it. If anything's above 500, the odds are good you're going to be adding a 9 in front of it. So one way is lower pressure, one way is higher pressure. So in this case, it's 1019.8. Kind of a typical pressure, average pressure. The other thing I want to look at is winds. A lot of you seem to have trouble with winds. So the winds are the barbs. If you were looking at this, notice it comes in on the northwest side of the circle. If you were just looking from the top, that means it's a northwest wind. So it's northwest wind, it's a small barb, it's 5 knots. Let's come over to the east coast. Notice here it's coming in from the northeast side. Northeast side means northeast winds. Again, it's a small barb, so it's probably 5 knots. There's not a lot of wind out here today. However, if you get down to the Chesapeake Bay, there's a little more here. We got a small barb and a bigger barb. So there's northeast winds at 15 knots. There. We've now figured out winds, wind direction and wind speed. Look at the circles. Almost all the circles are kind of cloudy today. They're covered in. And that's because it's a cloudy day most everywhere. If there was precipitation, it would show up to the left-hand side of this. And let me bring it down here a second. Maybe I can move this to a little bit area that might have precipitation on it. Okay, we have a radar on here, so maybe we can get lucky and find one, but really there's not much going on today in precipitation. Matter of fact, I don't see much at all. One of the things I did want you to notice is we have low pressure off the east coast of the United States. I showed you it in the satellite image. Counterclockwise wind flow. That's what you're seeing here. Big low pressure, precipitation with it. All right, with that, let's take a look at a meteogram. Meteograms, very simply, it's plotting dew point or temperature in the y-axis and time in the x. All I've done with the computer is take every single bit of an ASOS observation, and they come out every minute, and I've just plotted it here. So if I was looking at this and I ask you, where's the highest temperature at on this? Well, I see a couple places. I could be here, coming along. Oh, no, it gets a little higher right here. So the highest temperature literally is at 3:55 p.m. on January 29th. Hey, guess what? It's in the afternoon, mid-afternoon, like we usually say. So that was when the highest temperature occurred at this meteogram. When was the lowest temperature? Well, there's one possibility is here, and it's a little complicated. There could be another one right in here, and I think that's probably the one I would choose, about 37 degrees. So now we've taken the two. Oh, yeah, maybe I want to know how far apart the dew point and temperature were. Well, here we got the biggest one. This looks pretty big. 44 and 28. What is that? 16 degrees spread, 17 degrees spread. And at that point, we actually have a humidity, 53%. So it's relatively dry. Notice as they get closer together over here, the humidity goes up. We could look at another graph here. Say I don't like that one. I want to know what the wind is doing. So we'll do a wind direction graph. This graph has wind speed. It has gusts. There aren't a lot of them, but there are a few. And wind direction. It just has a dot for the wind direction. Kind of confusing, isn't it? But here we have east wind at 050. Anything, think of it starting as a compass at the top at 0. Anything, and you're going clockwise around it. So everything from 50 degrees is going to be on the right-hand side of that compass, are northeast winds. So we switch from northeast to north, north. We go to north wind here. And then all of a sudden, right there, we go to southeast. We had a wind direction shift. And notice, ever since then, we've been going southeast to east all the way along here. Not a lot of wind. The strongest winds were over here. We actually had wind gusts of 30 at that time. So, interesting you can see that information on that plot. I want to translate that into a surface weather map. We've talked and talked, and you're tired of hearing me probably tell you that you need to know the wind direction going around something. A high pressure always will have clockwise wind flow. Take a look. Here's a high down here. Winds are southwest, northwest, north, southeast, clockwise wind. Around this low that's developing out here, we have northeast, northeast. Over here, we have southeast. Look at this low. We have southeast out ahead of it, counterclockwise. One other thing I wanted to talk about here is looking at upper air. Upper air is just a plot of a temperature and dew point and wind with height. In other words, if I send a balloon up, we've talked about radiosondes and dropsondes, they measure temperature, wind, pressure, and they tell you what pressure they're at and what altitude they are. So literally I can relate a pressure to a height. I don't put that on this one. But here is 800 millibars. So I go across 800 millibars. And what do I get? I get minus 20 degrees for a dew point and a temperature of almost zero, probably about -2. So that is temperature and dew point. Pretty widespread between the dew point and temperature there. So fairly dry. Notice when the lines get close to together, that's where the clouds are. So all you're doing is reading down here and up to get a temperature or a dew point, and you're going to be able to see the 800 or 700, whatever level you're at. Over here, you're getting a wind direction at that. Higher up, higher winds. Up here, you have 50 knots of wind out of the southwest. Here, they're going more to the west, but you get a little bit stronger, maybe 50, maybe 65 knots. I want you to notice here you have southeast winds at the low levels, and then they shift to southwest. So you can see there's a definite change. We talked about how wind direction is going to change with height. So that's what you're seeing here. And finally, I wanted to look at advection. And I did this on a little tougher graph for you to read. I'm sorry. But the dashed lines are temperature. I want to look at temperature advection. We had that coming in the other week, when it got quite cold. We had very strong temperature and cold air advection. I also mentioned it in the video for the week. Let's take a look at it here. If I were looking at temperature advection right now, notice blue lines indicate negative temperatures. So the temperature is below 0 degrees Celsius. Everything's in Celsius metric scale. So with that, it's almost no temperature advection. Notice how the winds are blowing parallel to the lines here. So there's pretty much no temperature advection right here. And there's really not any real strong temperature advections anywhere on this map. There's a little bit of cold air advection going in here because we're pushing across isobars here. So you're getting a little bit colder here. Now, Further out here, on the other hand, lots of warm air is coming up, being pulled into this, so we have stronger temperature advection. What you're looking for here always is how the winds line up with the temperatures, the isotherms, how close the isotherms are to each other. If the isotherms are very close to each other, and we wind up having wind that's perpendicular to the isotherms, you're going to have strong temperature advection. If the isotherms are very spread out, or the winds are parallel, you're going to have very weak advection. This same thing can hold for pressure, and it can hold for moisture. They're the three principal ones you're going to look at. So that's what advection is. Advection is very important to understand. You'll be dealing with it a lot. So I hope you got a little bit out of this. And please don't hesitate to ask me any questions about the labs.